Spherical coordinates in 3 space. The spherical coordinates of a point P in 3 space are rho, theta, and phi. This is rho, theta, and phi. Where rho is the distance from P to the origin, and theta is the same as in cylindrical coordinates. Phi is the angle from the positive z-axis to the vector OP. And phi is always between 0 and pi. So it's not a full rotation, it's just half rotation. Again, let's write this down. Usually it causes a little bit of trouble. Rho, theta, and phi. And let's look at this. So this is the point P. You drop down a perpendicular. This perpendicular, if you point that, basically you get a reflection of P on XY plane by that perpendicular. Then you connect that reflection into with O, and then the angle that R makes with the x-axis, positive side of x-axis, is theta. The angle that rho, basically the vector OP makes with the positive side of z-axis, is phi. Now let's look at the GeoGebra app on this one. And so the point, let's say this one is point A, and then you connect point A to origin, and then look at the angle that connection makes with the positive side of z-axis. This angle is the angle phi. And then you drop down a perpendicular which hits the xy plane. That point down there is the reflection of A, and then connect that point to origin and you get angle theta. This distance between A and O is rho. So again, if you look from above as Z basically is perpendicular to U, then you can see that theta is the angle that normally we basically talk about in the polar coordinates. And the little r is the reflection of basically of the rho on the xy plane. And that's something nice to consider, basically. So let's do a few examples of obvious objects in polar coordinates. Rho equal to r defines the sphere of radius r. So let's say rho equal to 3, that means a sphere of radius 3 and center at origin. The ball of radius r is given by inequality rho between 0 and r, and theta between 0 and 2 pi, and phi is between 0 and pi. So that would be the equation of it. This is the description of it, basically. Points with phi equal to 0 are on the positive x-axis. If you remember, phi is the angle that made with the positive z-axis. If that angle is 0, we are on the z-axis. Phi equal to pi half is the xy plane. That's something that, and so different phis can give you completely different stories. Points with phi equal to pi are the negative z-axis. And so for all the other values of c, the equation, between 0 and pi, other than 0 and pi, half and pi, phi equal to c defines a nap of a cone. So how do we convert? Conversion to and from spherical coordinates. Conversion from spherical to Cartesian is these formulas. X is going to be rho sine phi cosine theta. Y is going to be rho sine phi sine theta. Z is going to be cosine phi. Cartesian from conversion from Cartesian to spherical is rho equal to square root of x squared plus y squared plus z squared. Tangent of theta is equal to y over x. Cosine of phi is equal to z over square root of x squared plus y squared plus z squared. Conversion from spherical to cylindrical is rho equal to rho r equal to rho sine phi. Theta is equal to theta. Z is equal to rho cosine phi. Conversion from cylindrical to spherical, rho is equal to square root of z squared plus r squared plus z squared. Theta is equal to theta. Cosine theta is equal to z over square root of z squared plus r squared. How does this conversion work? And remember, this distance, the blue distance, is rho, and here this angle is phi. And so if I want to find z from rho and phi, basically, here's the triangle. Z is this red. Phi is, true, phi is that, but also is the angle up here made between blue and red. So basically, z is going to be this rho. If this is phi also, so it's going to be rho cosine phi. So how do I find x and y? We found that z, because this angle right here is also phi. We found that z is going to be rho cosine phi. How do I find x and y? For x, to find x and y, I have to find r. But r also is in that triangle, so r is going to be this time rho sine of phi. And then x is rho cosine theta, so it's going to be, and rho, x is r cosine theta. Let's say r cosine theta. Therefore, x is going to be rho sine phi, which is r, times cosine theta. And similarly, y is going to be r sine theta. So basically, y is the formula for y is going to be rho sine phi sine theta. And so that's how, if you remember this triangle that is formed between rho, r, and z, then it makes your life a lot easier. Here's the z, here's the rho, and phi again. This is phi, but then this has to be phi also. And then going from there, you have to remember that you can basically convert. If you have r and theta is given also, you can find x and y. So you use rho and phi to find z and r, and then from there you can find x and y as well. Okay. So one described that r is basically r is going to be r is equal to again rho sine phi. This comes in handy because then also you can use it when converting between cylindrical and spherical. That's another way of using it. and y is rho squared is equal to x squared plus y squared. That's another thing that you can see, that down here basically this is y, this is x, so r is going to be x squared plus y squared, but in this triangle we have z and r and rho, and so you get rho is z squared, rho squared is z squared by that triangle plus r squared. But what was r squared? Was x squared plus y squared. This helps from remembering the actually how these coordinates relate to each other. Okay, now example time. Convert rho theta phi equal to 2 pi fourth and pi third to Cartesian coordinates. So what was the Cartesian coordinate? It was x equal to r is just rho sine phi and r cosine theta, y is equal to rho sine phi, which is r times sine theta, and we figured out z is equal to rho cosine of phi. Now replace everything. Rho here is 2, sine of phi, phi is this one, sine of is 2, and sine of pi third, that's phi is pi third, is square root of 3 over 2, cosine of theta, which is pi fourth, is square root of 2 over 2, and so you end up with square root of 6 divided by 2, and then here again 2, square root of 3 over 2, and square root of 2 over 2, and again square root of 6 divided by 2, and here 2 cosine of phi, cosine of pi third is 1/2, and you end up with 1. And so this is how you convert from spherical coordinates into Cartesian. Example 7, describe the surface. And this is an example from for conversion to and from spherical coordinates. And example 7, it's asking to describe the surface given by the equation in spherical coordinates. Now, I'm looking at this. The rho is going to be kind of messy. It's going to be square root of x squared plus y squared plus z squared. This sine theta, sine phi and sine theta look familiar, and sine phi cosine theta also looks familiar, but they are missing something. What are they missing? If I multiply that by a rho, then I get y for this one and I get x for that one. So what if I multiply everything by a rho? So I go rho squared is equal to 4 rho sine phi sine theta plus 2 rho sine phi cosine theta. Now what happened? Now this part is x. Oops. This part is y, and this part is x squared plus y squared plus z squared. Now I can rewrite it as an equation in Cartesian coordinates and see what kind of surface it is. So according to the computation that we did, multiplying everything by rho and then replacing and converting from Cartesian to spherical, we ended up with this. Now, this awfully looks like a sphere, but it seems like a shifted sphere. So let's try to subtract the 2x from this side, subtract the 4y from this side, and complete the square. If you complete the square out of this one, you will get x squared minus 2x and half of the negative 2 to power 2 added, that's 1, subtracted, y squared minus 4y, half of negative 4, which is 2 to power 2, which is 4, minus 4 plus c squared equal to 0. Now, what is what? This part is just x minus 1 to power 2, and this part is y minus 2 to power 2. And then negative 1 and negative 4 can go to the other side to form 5. And that's the sphere, basically. X minus 1 to power 2, y minus 2 to power 2, plus z squared equal to 5. So the center of the sphere is x equal to 1, y equal to 2, and z equal to 0. 1, 2, and 0. And then the radius of the sphere is equal to square root of 5. I got here question 13.7c. What are the Cartesian coordinates of the point with spherical coordinates rho, theta, and phi equal to 4, 0, and pi? Take a little break and compute the Cartesian coordinates for this point, and we do it together. So hopefully you found the values. Let's see, how do we go about this? And so what we need to find, rho and theta and phi is given. Now let's find x. X is equal to rho sine phi cosine theta. Oh, by the way, sine phi is just 0. So x is equal to 0. Same thing, y is equal to rho sine phi sine theta, and that's going to be equal to 0. What about the z? Z is going to be rho times cosine of phi. Cosine of phi is negative 1. Rho is 4, so this is going to be negative 4. So A is the answer. I got here question 13.7d. Which of the following describes the bottom half of a ball of radius 4 centered at the origin? And so take a break and solve and come back. So hopefully you took a break and solve. Here for all 4 options, rho is between 0 and 4. It's the bottom half of the, let's see, there's this, the bottom half of the sphere is around here. It goes all around. That means theta has to be between 0 and 2 pi. So this one's out. The next part is that we're saying bottom half, and phi from 0 to pi half is the top half. So phi from pi half to pi is the bottom half. So A again is the answer. I click your question 13.7e. Describe the graph of a spherical equation phi equal to 3 pi fourths. So let's take a pause and come back. So we're saying phi equal to 3 pi fourths. You're basically taking, let's say, let's write down, so this is pi half, and you go down this way, but then you take, let's just imagine you're holding a pen and going about the z-axis, which is another pen, and just turning all around at 3 pi fourths. What do you get? You get a cone and lower nap of a cone. That's D.